Section 6.3, Function Operations and Composition. So in this section we're really only going to be doing two things that are new, and we're going to be doing four things that shouldn't really be very new to you. How it appears might seem new, but for the most part the process shouldn't be new, and that the things that aren't new should be the addition, subtraction, multiplication, and division of two functions. The one that will be somewhat new will be the composition of functions, and then also determining a domain. And what we're going to be doing in this section, since we're going to be looking at equations algebraically, we need to think about what x values might not make sense, or we need to determine what are the only x values that do make sense. So for example, you can't have a 0 in the denominator. You can't take the even root of a negative number, so you can't take the square root of -4, for example. And then remember, if this is not new to you hopefully, that if we use a square bracket it means the endpoints are included, and if we use parentheses it means the endpoints are not included. So, and also when we're dealing with infinity we always use parentheses because it's such an abstract number. So let's start with the composition of functions, or sorry, the operation of addition on functions. If we're going to find the sum, then we need to take the f function, which is x plus 5, and add to it the g function, 3x minus 4. Well, this is just combining like terms, so we get 4x plus 1. When we think about the domain, are there any values that you could not put in for x? I can put in any negative number, I can put in any positive number, so I need to go from negative infinity to positive infinity. This would be all real numbers. Now let's subtract. Again, we take the f function, but remember that when we're subtracting, we need to make sure that we distribute that subtraction across the whole function. So make sure that you're putting your second function, or the function you're subtracting anyway, in parentheses. When we distribute the negative, we get minus 3x plus 4. Then combining like terms, we'll get negative 2x plus 9. Again, we can put in any number, positive or negative, into our x value, so our domain will be negative infinity to positive infinity. This next example, it's the same idea. We're just going to be combining like terms basically. So we're going to take our f function, 4x to the 1/2, and we're going to add our g function, 2x to the 1/2. Well, we have the same variables raised to the same power, so altogether we have 6x to the 1/2. In determining the domain, we need to remember that x to the 1/2 actually means the square root of x. And so, since we're taking the square root, we have to deal with just positive numbers. We could put in 0, but that's the smallest number we could put in. So we're putting in 0, and it's included, so we're going to use a bracket, and we're going to go all the way to positive infinity. When we subtract these two functions, again, we're just subtracting like terms, so we're going to get 2x to the 1/2, and the same idea holds that x to the 1/2 is the square root of x, and so our domain will be the same for this example as well. So those two examples were finding the sum and difference of two functions. Now let's move on to finding the product and the quotient. So given the x function, x plus 5, and multiplying that by the g function, we have to remember that we have to multiply everything in the first parentheses times everything in the second parentheses. Some of you may know this process by foiling. Combining like terms, we'll get 3x squared plus 11x minus 20. Again, when we think about the domain, is there anything that we cannot put in for x, either in the original two functions or in our resulting function? And there's not. We can go from negative infinity to positive infinity. When we divide our two functions, again, we're going to take our f function, divided by, remember we could write this as a fraction, the g function. We can't simplify anything. We can't cancel out the x's or simplify anything because we have addition and subtraction in the numerator and denominator. So that is our simplified function. And when we think about our domain, we have to realize that our denominator cannot be equal to 0. So we're going to take our denominator and make it not equal to 0 and figure out what x cannot equal. X can equal anything else. The result will just be a fraction, so we can go from negative infinity all the way up to, but not including 4/3, but then we need to combine that with 4/3, again not included, up to positive infinity. So this is how we would write that in notation to determine what the domain is. And the next and another example demonstrating the product and quotient. So our f function, 2x to the 1/3, times the g function. Remember, when you're multiplying common bases with exponents, we can add our exponents. So we'll get 2x to the 5/6. Again, when we think about the domain, remember that x to the 5/6 means the 6th root of x. Again, that's an even root, so x has to be greater than or equal to 0. Again, 0 can be included though, so we're going to go from 0 with a bracket to infinity. When we divide our functions, remember that we can subtract our exponents, so we get 2x to the negative 1/6. Remember that the negative 1/6 is on only the x, so we need to take care of our negative exponent. It'll be 2 over x to the 1/6. And for our domain, again, like we did in the last problem, so our x has to be positive, but also remember that our denominator cannot be equal to 0. So in this case, our x has to be strictly greater than 0. So we're going to use parentheses on the side of the 0 because it's not included up to infinity. And now the composition of functions. This is the thing that's new. This is read f of g of x, where the bottom one is read g of f of x. And so it's basically just repeated substitution. Whatever's on the inside, you need to take that function and put it into the outside function. So in this first example, f of g of x, the first thing we're going to do is we're going to take f of, and then g of x is x squared. So we're going to replace the notation of g of x with what it is, which is x squared. And now we're going to plug that x squared in the x spot in the f function. In this case, there's not really any simplifying that we can do. We can write it just as 4x squared plus 1. Now let's take the composition the other way, g of f of x. So this time we're going to take the g of function, and we're going to replace notation-wise, f of x is 4x plus 1. So we're just going to replace f of x with what it is, 4x plus 1. We're going to take that and plug it in for the x into the g function. 4x plus 1 squared, when we FOIL this out and combine our like terms, we'll get 16x squared plus 8x plus 1. And now let's do the same function, but let's take f of x. So again, we're going to take f of, and what is the f of x function? 4x plus 1. We're going to plug that whole 4x plus 1 back in for x in that same function. So 4 times, plugging that 4x plus 1 in for x, plus 1. Distribute the 4, we get 16x plus 4, plus the 1, simplified as 16x plus 5. Again, a different kind of function, one dealing with exponents, but the same idea. Let's do f of g of x. If you think you've got the hang of this, why don't you pause the video and try to do it on your own, and then come back and I'll still walk through it, or if you've gotten it right, then you could fast forward it. So f of, and we're going to plug in g of x, which is x plus 1, and now we're going to take that and plug it into the f function. So x to the negative 2. Let's take care of the negative exponent. Simply means we put it on the denominator and make it positive, and that would be our simplified answer. And the next one, g of f of x. So g of, we're going to plug in x to the negative 2, and now we're going to plug that in for the x. So x to the negative 2 plus 1. Again, let's take care of the negative exponent. 1 over x squared plus 1. Let's do the same thing, f of x. So f of x to the negative 2, plugging that whole thing back into the same function as x to the negative 2 to the negative 2. Remember, we multiply our exponents. Negative 2 times negative 2 gives us a positive 4, so we really don't have to take care of any negative exponents. The last example, f of g of 4. Well, we're given a real number, so let's just go ahead and find g of 4. plugging 4 into the g function, 4 squared plus 3 times 4 minus 9. And simplifying that, we get g of 4 equals 19. So now we're actually finding g of 4. Since g of 4 is 19, we're finding f of 19. Plugging 19 into the f function and simplifying it, we find that f of g of 4 is 64. In this example, g of f of negative 5, again, we want just f of negative 5, so let's go ahead and do a sidebar and find that first. F of negative 5, plugging negative 5 in for the x, and simplifying, we get f of negative 5 is negative 8. So in place of the negative 5, we're going to plug that into the g function. So g of negative 8 squared. Again, be careful. A very common mistake is to plug this into your calculator as negative 8 squared without any parentheses, and your calculator will give you negative 64. Make sure you realize that this is negative 8 squared, which is a positive 64. Simplify this, we get 31. So g of f of negative 5 is 31. And the last example, f of g of x. So we're going to take f of, plugging in the g function, x squared plus 3x minus 9. Now we need to plug that whole thing in for the x in the f function. So 3, this is my x, plus 7. Distributing the 3. Don't forget to add the 7. Combining those like terms, we get 3x squared plus 9x minus 20. Make sure if there's anything that you didn't understand, if it was the domain notation or exactly how to find the domain, the composition of functions, please make sure you come to class with any questions. And we'll see you tomorrow in class.